So today we're talking about the ideal gas law. Now we've already done the combined gas law and Boyle's law, Charles' law, and the temperature pressure law. So we already know how to handle things when we've got one amount of gas undergoing changes to their conditions. The ideal gas law we'll use in those situations where we're not changing conditions. We can also use the ideal gas law when we're trying to figure out numbers of moles or numbers of particles of gas. Now if you think about inflating a balloon, so you're blowing up a balloon, every time you put a breath of air into that balloon, the balloon gets bigger. Now when you do that, yes, you're increasing the volume. You're probably not increasing the pressure because that's what's causing the balloon to expand, but what you're doing is you're increasing the number of particles. You're putting more stuff into that balloon, and then as you increase the amount of stuff, the volume goes up. So we could start working with a mathematical expression for that as well. However, let's first talk about what an ideal gas actually is. And the short answer to it is it's not actually anything. So anytime you see the word ideal in science, it means here are a set of conditions, or here's a simplification of reality. For us, though, most gases will show ideal behavior under some conditions, but not all conditions. We're going to ignore those times when it won't, and we will just assume that gases are always ideal. But if you've been in physics, you talk about a system that has no friction. That doesn't actually exist. We can get systems with low friction, but never none. So an ideal gas has these properties, and we don't really need to write them down because you're never going to be asked to define an ideal gas. But I want you to take a quick look at a few of them. So they're identical molecules, which means we wouldn't have any isomers or anything else like that, or that wouldn't be significant. Particles have a mass but no volume. Now I've got no in quotation marks. If you think about it, Charles' law says that as I reduce the temperature, I reduce the volume. So if I reduce the temperature to 0, Charles' law would say I'd have a volume of 0. Well, that doesn't really make sense because the particles themselves must have volume. In reality, yes. Under ideal conditions, no. So we ignore the size of the particle itself. They obey Newton's laws of motion. Okay, in a lot of cases they're going to. And the other one that's going to be important for us is this one here. They do not interact. Now again, I don't need to write it down, but what it means is at any temperature, any pressure, any volume, those molecules will not experience any intermolecular forces. And that's just not realistic because if you cool a gas down, it will turn into a liquid. We're going to ignore that. So we don't need to worry about what these properties are. Just understand that most things we might say ideal, but reality is going to be a little bit different. Unless you're talking about something like bacon. That's ideal. Alright, so here's what the part we do need to know, the ideal gas law. There it is. Now that, of course, needs some explanation. So, P in that, you probably guessed, is pressure. Now it's really important, although for us it's not going to make any difference because I only give you pressures in kilopascals. But there are other ways of measuring pressure. For us, it will only be kilopascals. V is the volume in liters, and that's a little bit more important for us because it must be in liters. If I give you a volume in milliliters, you will have to convert it. N is the number of moles. You will either be given the number of moles, asked to calculate the number of moles. R, a gas law constant. And this is 8.314 liter kilopascal per Kelvin mole. If I just write that unit a little differently, liter kilopascal over Kelvin mole, we see that we've got all the units for everything else. So I've got liters, that's my volume, kilopascal, that's my pressure, Kelvin, temperature, and then mole is N. So the job of these units is to make all the other units work out. All by themselves, they really don't have a lot of meaning. If you had other pressures, millimeters of mercury, atmospheres, psi, this number would have to be different, but we're not going to have to worry about that. And the temperature in Kelvin. Okay. How do you use it? Well, we often are going to be using it in its converted form. Now, you don't need to write down each one of these things, but we're going to have to be able to solve for pressure, or solve for volume, or solve for temperature, or solve for a number of moles. You don't need to write all those down. On a test, on a quiz, on an exam, I will give you the ideal gas law, but then you need to be able to solve it out. But what you might want to do is make sure you understand how each one of these rearranged versions comes about so that you can figure them out when you need to. All right, so a couple types of questions. There's about 3, maybe 4, 5 on the outside kinds of questions that you're going to be asked, although 2 or 3 of them kind of overlap. One of them is solving for one of those items: pressure, temperature, volume, numbers of moles. Solving for something. So here's a question. You're given the number of moles, you're given a volume, and you're given a temperature. So you have almost all of the pressure, volume, number of moles, RT. And of course R, you're not going to be given R in the question. You might be given R on the front of the paper. But it's a gas law constant, so it's always the same. We don't have to worry about it. All we have to remember is 8.314. So I don't know pressure, but I do know volume. Must be in liters. And I do know the number of moles, and I know R because that's a constant, and I know temperature. And yes, it has to be in Kelvin. So put that into our formula. Now I like to rearrange the formula first. Maybe you don't, and that's okay. Eventually you'll have to. Put in what we know. I left the units out just so it wasn't quite so cluttered, but typically I'm going to have the units in. So I've got nRT divided by volume, and I end up with the pressure. Now the pressure will automatically be in kilopascals, and that comes out of these units from R. So that's one kind of question you'll be asked. And you could be asked to find temperature or volume, and so on. Different kind of question is when you're given a mass. So what volume would a mass of this gas occupy at SATP, which of course is standard ambient temperature and pressure. So start with my ideal gas law. What do I know? I know the pressure, because that's standard ambient pressure. I don't know the volume, because that's what I'm asked to find. And do I know number of moles? Well, not directly, but I do have a mass. And if I have a mass and a chemical formula, I can calculate numbers of moles, mass over molar mass. So now I know how many moles. And I have a gas law constant, and I have a temperature. Standard ambient temperature is 25 degrees Celsius, which is 298 Kelvin. So doing the same thing now, calculating the volume, well, I like to rearrange first, putting it in, so I've got my number of moles, I've got my gas law constant, I have my temperature, I have my pressure, solving for volume is 360.5 liters. So one additional layer to that where I'm not directly given numbers of moles. This question, finding the molar mass of the gas, and that's going to become kind of important. Gas sample has this mass, occupies that volume at that temperature and that pressure. So same place. What do I know? I know the mass. And I know that molar mass, by the way, I'm one step ahead of myself. Molar mass is mass over number of moles. And if I didn't know that, grams per mole. So my units tell me. See how important units are? Anyhow, I'm going back to here. I know the pressure I was given that in the question. I know the volume I was given. I don't know the number of moles, but I do know the R value. Always know that. And I know the temperature. So I'm solving for number of moles. And when I do that, I put all those numbers in, I get 0.0027 moles, but that number of moles corresponds to that mass. So molar mass is mass over number of moles, so it's 0.081 grams divided by 0.0027 moles, and I would have 30 grams per mole. This kind of question will actually will actually allow us to bring back something from the past. There's a kind of question we did back in unit number 3 where I always told you the molar mass. Now I can ask you to calculate the molar mass, and you'll be doing this. So the question will be a little bit of a blast from the past. Anyhow, that's all there is to it. The really 2 important things to keep in mind is identifying what information you're given and what you're not given. Is there a way to calculate what you're not given if there's 2 things? Like if you look back at the previous one here, I wasn't given number of moles and I wasn't given volume, but I've got a way to calculate numbers of moles. And then the other thing, always, units. Pay attention to the units. What units do you have? What units do you need? Do you have a way of calculating the units that you need? That's it. That's all there is to it. Talk to you in class, and hope this works out for you.